Hi everyone. So this is our first video over Chapter 8, Conservation of Energy. This video is going to be over conservative and non-conservative forces. So first, let's talk about a pendulum and the work that's done by gravity. So if we have a pendulum made of mass m attached to a light cord L, if it's released from an angle theta with the vertical in the absence of friction, derive an equation for the kinetic energy of the sphere at its lowest point. So let's get a drawing here. Okay, we've got mass m, length L, okay, and that is at angle theta. Okay. So that's what we're dealing with here. Now we want to derive an equation for the kinetic energy of the sphere at its lowest point. So that means that we're going to want work. And if we want work, we should get some forces. So let's get a free body diagram real quick. Here we have our tension. Here we have angle theta. And here we have mg. Now, I do want to remind you that when we move in circular world, we don't use x and y. We're going to use radial and tangential axes. So the radial will be right along the tangent, or right along the tension, and the tangent will be perpendicular to that. There you go. So these are the axes that we are going to use to find the kinetic energy of the sphere at its lowest point. Now you'll notice here that our mg has a component in both directions, whereas tension only has a component in one of those directions. And we have our angle theta right there. So if our velocity, right, we're talking about kinetic energy, our velocity at the bottom is going to be going purely in the tangent direction. What we want to do is we want to analyze the two forces that have to do with its motion, and we're going to incorporate the theta in the image. So the two works, right, because we're going to use work kinetic energy theorem to find this. If we use the two works that we have to get our delta K, okay, we have the work of mg, and we'll just call that the work of g. And then we have the work done by tension. Well, as we're looking at this, we can see that the tension is at a right angle to our displacement. It's also a right angle to our kinetic energy. And if anything is at a right angle in kinematics or in work or in energy, it's not going to affect what it is perpendicular to. So we can actually disregard the work done by tension. Now, if we want to find the work done by gravity, we need to look to see what component of gravity are we looking at. Well, here, if we're using the same theta, right, this would be mg sine theta. So if we want to find the work done by mg sine theta, what we'll do is we will integrate it from theta to 0, right, as it does that work swinging through its arc of mg sine theta dr. Okay, and that's as it's swinging through the arc. Now, this part gets a little hairy. What does that dr do? Well, let's show you this real quick. If we look at these 2 points, we've got theta, and we have theta equals r over r, which is so inconvenient, right? But this is the common equation that I've seen used. Little r is the radians of arc, and big R is the radius. Now, if this object is swinging, that means that our radians and our angle are actually changing. So we can use calculus to analyze this. But as an object swings, the radius doesn't necessarily have to move. Now, it could be moving, and that is a very different problem. But here, if we have our radius that is set in stone, the string is not going to change its length, and the object will not bob through its swing, right? Let's say it's a smooth swing. The radians and the theta will change as it swings. But we have an issue here. We are integrating with respect to dr, but our bounds are with respect to theta. So what we need to do is we need to solve for dr in terms of d theta. So let's move back over here. If we solve this guy for dr, we get r d theta equals dr. Now in our problem, you will also notice that our radius is not r, it is l. So this would, for our specific problem, would be L d theta equals dr. So we can actually plug that in right here. We will have the integral from theta to 0 of mg sine theta L d theta. So now we can integrate with respect to theta. So to integrate sine, okay, the integral of sine is negative cosine. And this is an important circle for you to know. If you have, we've got sine theta, right? And if you take the derivative of that, you get cosine theta. If you take the derivative of that, you get negative sine theta. And if you take the derivative of that, you get negative cosine theta. And if you take the derivative of that, you're back to sine theta. So blue is the derivative. However, if you integrate sine theta, you get negative cosine. Integrate negative cosine, you get negative sine. Integrate negative sine, you get cosine. And integrate cosine, you get sine. So green is going to show your integral. Blue is going to show your derivative. But if you look at our green arrow, the integral of sine is negative cosine. This is a very important circle to remember. That's what I use when I need to do a derivative or an integral of cosine or sine, which happens more frequently than you'd think. So if we want to do this, we would take the integral of mg sine theta L. Okay, so mg and L are variables. They will sit this one out. Then the integral of sine is negative cosine theta from theta to 0. So this will give us mgl from, so you do final minus initial, right? So you've got, actually, you know what, let's move that negative out. So that will be a negative mgl, just to make this simpler. Okay, negative mgl, cosine of 0, right, is 1. Then we have cosine theta. Okay? So we have negative mgl times 1 minus cosine theta. Now, here is where physicists will do specific math operations, not to make it simpler, but because we have a specific goal in mind. What we're going to do is we're going to distribute through that 1 minus cosine theta. We will only distribute one variable. What we're going to do is we're going to distribute, don't forget the negative, mg, we will distribute L minus L cosine of theta. Now, why do we do that? Great question. So let's look at what we have here, right? We have L, and here we have this length right here, which is L cosine theta. If you take the entire length L and subtract L cosine theta, what you get is this guy here, which is your delta y. This is basically the height change of your object. So if we say that L minus L cosine theta is really the delta y of an object, you could say that the change in kinetic energy, which is what we're solving for, equals negative mg delta y. And this is something we'll get into later on in this chapter, but mg delta y equals gravitational potential energy. So what this is showing us is that the gravitational potential energy of that pendulum at an angle theta, as it comes down at its lowest point, has converted all of that potential energy into kinetic energy. So we can see that there. So that is what happens if we try to find the kinetic energy of the sphere at its lowest point. You're going to find that it's equal to your gravitational potential energy. Now let's look at our follow-up questions. First, number one, how much work does the tension do? Well, since tension is perpendicular, remember this is a pattern we've had through work, right? If work has something that's perpendicular, it does no work, right? That's going to be the same for energy, because work and energy are going to go hand in hand through chapter 8. Now, that was also a thing for kinematics, right? For example, if you've got a projectile, right, the acceleration in the x will not affect your velocity in the y. You have to have acceleration in the y to affect the velocity in the y. You have to have acceleration in the x to affect the velocity in the x. So this is a common pattern that we're going to see throughout a lot of our physics. Now, we will hit a point where we will start using sine theta instead of cosine theta for our equations, where we have, work is FD cosine theta. We will hit a point where we will use sine theta, where if you desire a perpendicular relationship and a parallel relationship yields a zero. But we will cross that bridge when we get there. Okay, next slide. Okay, now we've got conservative and non-conservative forces. So what are the two most important properties of a conservative force like gravity and its work? Well, we've got two very important properties. Number one is that the path taken doesn't matter. It does not matter. Okay? So remember that pendulum. We traveled an arc, right? But when we found when we were talking about the gravitational potential energy, all it really cared about was this change in height. Now, if you think about gravity on our planet, right, because I can imagine most of your potential energy problems will take place on planet Earth. Earth's gravity just cares about how far away you are from the surface. For example, if you go to the International Space Station, right, you are now leaving the Earth's surface, and when you get far enough from the surface, you're going to experience very little gravity. As you start moving towards the surface, you're going to experience more and more gravity. But it doesn't matter the path you take, right? Say you're trying to land a plane, right? Your gravity is technically weaker when you're up in a plane compared to where you are on the surface, because you're a distance away from the surface. So if you land your plane, right, it doesn't care if you land your plane directly or if you take a lap around the planet first and then land your plane, right? It only knows that the change in work done by gravity is just the change in height. It doesn't actually care the path you took. Okay? So path does not matter. That is rule number one. Rule number two, let's use black again. Rule number two is that work for a cycle is zero. Work in a cycle is zero. And we talked about that, for example, with the wind turbines, right? Or if you run a 5K, right? It cares about your displacement, not the path you took, but it cares about your displacement, the distance between your initial and final. Okay? It doesn't matter what the initial and the final were. It just cares about the difference between your initial and final. So work in a cycle is zero. And this is for specifically conservative forces. Okay. Now, let's talk about a non-conservative force. Okay. A non-conservative force like friction. So if we look at these two paths an object took the blue path and an object took the red path. Does work done by friction depend on the path followed? So if we look at the object that took the blue path and the object that took the red path, Which object lost more energy? Because friction, takes away energy, it slows you down. Which object lost more energy due to friction? Well, red will lose more energy. But how does that make sense? Because we just said that the path taken doesn't matter. Well, that is because friction is non-conservative. It is not going to conserve energy. So if you think about friction, right? Friction cares very much about the path you take. For example, if you want to, say you want to move 3 feet away from your desk, okay? You move those 3 feet by skidding your shoes or skidding your socks, right? We're going to skid socks on the carpet and generate some heat from friction. Now you skid your socks 3 feet away from your desk. You probably generated a good amount of heat. Now let's take a lap around the room and end 3 feet from your desk. You're going to generate a lot more heat. Your feet will probably hurt by the end of it from all the heat and friction, but you end in the same spot. Friction cares about every little scraping distance that you have where you're rubbing against that solid surface. All resistive forces are like that. Water is the same, right? If you want to travel through water, the water isn't going to think, oh, you're ending over there. Well, let me just kind of average this out for you. No, it's going to resist you every molecule of the way. Every molecule of water that you run into, you're transferring your energy into that molecule. Same for air resistance. Your air resistance is your energy colliding with those air molecules, and those air molecules now take away a little bit of your energy. They don't care where your start and end point is. They're not going to average out and say, oh, well, if you're going to end over there, I'll just make this easier for you. No, it cares about the path that you take. It cares about every molecule that you run into. So non-conservative forces break these rules. Okay? Non-conservative forces, they do not follow the rules. So these rules that we've got up here, the path does matter for non-conservative forces. And a cycle can lose energy if there's a non-conservative force. Most of our pendulums that we talk about, right? A pendulum, we usually say, oh, absence of friction. So it can just sit there and sway forever, right? However, if you've got a pendulum that does have friction, if you cycle one time, it might return pretty close to its starting point. You may not notice a decrease in energy. But if you let that cycle 5 or 10 times, you might have a pretty low height by the end of it. That's because you are losing energy, even though it's a cycle, right? If we say absence of friction and you watch a pendulum go back and forth 100, 200 times, you would say that the work that it started with on this side is the work that it ends with on this side, because there is a non-conservative force. But as friction or air drag work on the pendulum, it's going to lose energy even though it's cycling. So work in a cycle does not equal 0 for non-conservative forces, and the path taken does matter. Now, just to drill in this point, which one do we ignore the detailed path for? Gravity, friction, or both? We ignore the path for gravity. Friction, you can't ignore the path. Every tiny distance that you rub against a surface or go against water or air or any kind of resistive force like that, it matters. Okay? So that's the difference between a conservative and a non-conservative force. Now let's talk about work from conservative forces being stored. So energy can be stored as potential energy. So so based on this pendulum idea, okay, let's be super clear about the connection between work done by gravity and gravitational potential energy and the change in gravitational potential energy. So notice these are different things. Okay, so I'll write these off to the side. We have the work done by gravity, and then we have the change in potential energy. These are going to be very different. So let's solve. Let's do some math here. Work done by gravity. Okay, work done by anything is the integral of the force. Let's get a better F than that. The integral of force along some displacement, right? Well, let's say that's really the integral of our force of gravity, mg. And mg only travels in one direction, that is dy. Okay, no matter what free body diagram you're doing, no matter what complex incline you've got, gravity's always down, right? And we will integrate from some initial y naught to some final yf. Okay? So if we integrate this, you get mgy from y naught to y final. And this will give you the equation that we actually had earlier, mg times y final minus y naught. We actually saw this before right down here. You've got mg times delta y. So this is going to be a common occurrence. Okay, this mg delta y, okay, that is actually the change in potential energy. If you have a change in height, you will change your potential energy. So this goes right here. Mg delta y, or expanded, would be mg y final minus y naught. And we will show that that is an important equation. Now, if you want instantaneous potential energy, okay, then you just want to give it a specific height, right? That would be shown for the potential energy of gravity. That would be shown as mgh. It has a set height at a set instant, and that is the work done by gravity at that instant. That is also very important. Okay? That's the relationship that we have between the change in potential energy and the instantaneous potential energy. Now, for some deep conversations. Where is potential energy of gravity equal to zero? So in an absolute sense, more on this in chapter 13, where could the gravitational potential energy equal zero? So if we think about gravitational potential energy, gravity depends on a couple things. It depends on the masses of the two objects. Okay? It also depends on the distance between those two objects. And then it also depends on the gravity constant that Newton discovered controls the equation. But if we're going to look at the scenarios, right, the gravity constant, that's constant. So it's not going to change from instant to instant. So the things that can change are the masses of the two objects and the distance. So in an absolute sense, how could you have potential energy equal to zero? Or you could have a mass approach zero mass, but that kind of eliminates the object, right? So one way is to have your distance approach infinity. As you get infinitely far away from the object, its gravitational effect on you is going to diminish to zero. Now, in a universe full of objects, that's very hard to get infinitely away from everything. You can't do that without leaving the universe, and we haven't figured out a way to do that yet. So you can get infinitely far away from one object, but then you're probably going to get infinitely closer to another. So but that's a pretty nice debate for another time. Now, in a practical problem-solving sense, when we're actually trying to solve a physics problem, when is the potential of gravity going to actually equal zero? Okay? So we actually get to define in our problem where that's going to be. This is called the ZPL, or the zero potential level. I marked out the word zero. Zero potential level. What is the level at which you consider there is zero potential? Now, the fun part about this is that if you do the math appropriately, the ZPL is arbitrary. It doesn't actually matter where you put it. because if you do the math appropriately, you're going to get the same answer no matter what. We will actually go into more in our next video, which is all about the zero potential level. But no matter where you put it, the problem is going to work itself out as long as you do the work appropriately. Now, there is a right and a wrong place to put the ZPL, because your goal is probably not to make the problem as hard as possible. You probably want the problem to be as easy as possible and as fast as possible, because physics, we usually have to prepare for some kind of exam, taking stuff like the AP test, and you don't want to spend all day because you put the ZPL in the wrong spot, and now the problem is harder than it needs to be. Okay? So it's arbitrary in the sense that the math will work no matter where you put it, but it is not arbitrary in the sense that there is a right and a wrong spot, because we all have goals in mind, and it's not to do physics, one physics problem all day. Now, we will go over more of this in our next video, where we can talk about what is the ideal spot to put your ZPL, and is it really arbitrary? Does the math actually work out no matter where you put it?